Hello and welcome to this week's instalment of Python Live, powered by Amicus Recruitment and the live series. Now, for those of you who don't know who Amicus Recruitment are, we are an IT specialist recruitment agency that focus on three key areas of IT, that being Python, JavaScript and Golang. Now, my name's Jordan Hayward and I specialize in recruiting across the Python market, specifically within Austin, but also remote opportunities across the US as well. I'll be your host for this evening, and today I'm joined by the amazing Meltem Ballan. Meltem is an AI and machine learning expert with a career spanning over 20 years. She's worked for some huge organizations, including General Motors and EY, and over the past year, she's founded her own small consultancy firm providing AI services to a range of clients. Now, Meltem will be given a brilliant talk on computer vision today, which I'm sure everyone will take a lot from. Now, a couple of housekeeping rules. As ever, this webinar is interactive and there is a Q&A tab at the bottom of your screen. So if you have any questions throughout, please do put them in there and myself and Meltem will get to them during the course of the presentation. So we are running a few minutes delayed, so I'll conclude my introduction there and hand over to Meltem herself. So welcome, Meltem.
Hi, Jordan. Thanks for inviting me today. It was kind of a bumpy road, but we are here. And a little bit about myself that you might not be able to find on LinkedIn or any place else. So I've been in computer science since I was 12. Actually, I was watching Mission Impossible, and I decided that I will be in this amazing world of the fingerprint recognition. And the first thing that my parents did bought me Chinese ink, and I started to collect the fingerprint. And that was the starting point of my career in computer vision. And later on, I decided to really follow my passion a little further, maybe a little bit about my my own problems with the developmental disorder. And then I became a neuroscientist, but everything turned me back into this world that I constantly deal with the images and the patterns, and I never got to work on the wonderful world of the AI with the beautiful data. So that's the pipelining process that I dealt over and over throughout my career in computer vision and feature extraction. So usually my talks don't have an outline, but I put the terms side by side here because I want to give you some basic information about like what is an image, how we define it, what are the formats, and what we are even starting with. And I'll talk about little bit resolution, DPI, PPI. Those are all coming from different disciplines like printing and camera, movie industry, but they are, at the end of the day, is the same terms. And I'll talk about some my favorite terms like image feature and illusions, and I'll get back into digital image and image processing. Then I'll talk about the open source tools because we know about Python, but there are other tools that you can leverage, and maybe you can enrich the open source Python libraries for next generation computer vision and image processing engineers. I'll talk about thresholding and morphology. I'm sure if you like the set theory, you'll like the morphology topic. And I have a little bit of a bonus that I don't know whether I can come here. I can give you that background, but I will share my slides. So I'll talk about the convolutional neural networks and a little bit about the deep counter as a basic deep learning algorithm. Let's start with the house cleaning and like some fun factors. You know, our world is definitely cluttered with the data, and usually the data is not clean. The second thing is that, as I mentioned, I never got to spend time on those beautiful algorithms. I clean and prepare the data every day. And focus approach, you know, this is the kind way they said it, Bayesian approach, but I call it bogus approach. The simplistic approach to the images are the best approaches, and big data is not the solution. It's just a tool for the solution. So I see some Q&A, but I don't think. Okay, so somebody is asking about the gas counts.
Yeah, I'll come back to that shortly. No worries.
Okay. So let's talk about, so I want to come back to today, but I want to talk about a couple of favorite topics. One of them is the beginning of image processing and where it started. Okay. It all starts obviously with the research and, more important, the military. So the first terminology for image processing started with the Bell laboratories. They were looking for some jet propulsion studies, and they were looking for some utilities, and they started to coin this word of image processing. They started to look at the images, and then they started to label the certain characteristics of the images. Later on, those handwritten images were put into computers and the dedicated hardwares. If you're old enough, you remember the sound system. So we are talking about those huge computers, huge hard drives. So in the 70s, we were dealing with those. And 1975 is the turning point, revolution in the image processing, because we started to develop color TV technologies. Then 2000, with the internet turning point, the crashes, we started to have fast computing and the processor. So, you know, it was this dust that everybody was talking about and nobody was trusting. But after the dust settled, we had less players, but more serious players. So we ended up having fast computing and processing power. And since 2018, we started to talk about big data, and social media is one of the biggest turning point in image processing, because we started to take those images, started to analyze our customers' behavior. So it became more of a external factor forcing the changes inside of image processing. And by talking about history, I have definitely talked about Lena. Lena changed most of the traditional computer vision scientists' way of thinking. That picture that she's holding is the picture that everybody tested their algorithms, from MIT to the small institutions. Everybody tested the quality of their algorithms. Unfortunately, you know, nowadays we talk about the gender, we talk about like where all this came from. But Lena was actually a prostitute, and then her figure was so clear that per image can be used, these edges that you see can be used in a lot of studies. She didn't get any money other than this picture in some porn magazines that was paid. And later on, I think it was like 2010 or so, she came out and then said that, you know, she felt used all those years, and she's a grandmother right now, and she doesn't want to be used in these studies. So I want to thank Lena, and for the last time, I'm gonna use some of the Lena images here, but I wanted to give this story because it is important how we are thinking about the gender equality and how we are approaching the image processing and technology nowadays. So the image, when we talk about image in the quantitative way, we talk about the format, resolution, image features, and digital images. So I will touch all those starting from the image formats. I'm sure everybody is familiar with the JPEG, GIF images, PNG, and TIFF. These are the most common formats that we use in the image processing. And nowadays, obviously, with the computation power, neuromorphology, and the edge computing, this list goes on and on. But these are the core of the image processing formats. So how good your image is going to define how good your algorithm is. So in the computation, we talk about the dot per image, and that's also gives you the quality of your image, resolution of your image. And dot per image also interchangeable to pixel per inch. So these calculations, you don't need to think so far about these, because open source algorithms here, you can see that you can do it in Python and check your DPI, PPI proportions with your images. But make sure that when you are building a study, your image format is representative. So all your images are in the same DPI or in the same resolution. So this is the first topic that I wanted to point out. And the other one is the digital images. So when you take a camera picture, you see my face, but in the computation, it is nothing different than just numbers between 0 and 2055. So this is kind of a magnification of the rat's noise. This is also a very common usage for an image like that. And then you see the pixel intensity value on the left-hand side. So this is also very interchangeable usage. And then let's get back into some of the image theories that has been used, and sometimes it's actually the topic of the puzzles. But I want to say most successful algorithms are built upon features of scenes and images, like patterns, reoccurring patterns and depth and the size. And how we address this has a couple of approaches. Like one of the first ones, but the most complicated ones, are looking at the fractals in the images. Like this is from my parents' yard, and this is my fun image to work. So this image has a lot of different patterns, a lot of corners, and even like the freckles on those apricots have some fractals in it. So what you do is that you take this image and then slowly but surely start dividing into small pieces. And then you start talking about the theories behind it. One is scalability, one is the depth, one is the equality of the smallest fractal that you're seeing. The first image is non-fractal because like whatever the partition, the part you take out of your image is the same. So the corner of this elliptic image is going to be the second image. And if you take that same corner, you're gonna see same elliptic image. So this doesn't have any fractal because the smallest piece is gonna look always the same. But when we look at the second image, we have some size and scalability. So every time you cut small pieces, you will be ending up taking different patterns. I highly suggest that if you're interested in this, Larry Leibovich, he was my professor at the PhD in Florida Atlantic University. He has a very simplistic book. It is almost like a manga book that you can read through and understand the fractals. And later, if you stay a couple more slides, I also provide you with a GitHub page that I really like. You can look at the fractals and start implementing your own algorithms. So this is an image illusion, and there are a couple of historical image illusion techniques that I want to touch quickly here. One is called the Shepherd's table, and Shepherd's table is a physical illusion. Simply, both tables are in the same size, but from the distance and the angle, we see that these two tables have different dimensions. In reality, these two tables have the same dimension. So why is it important is that, you know, you're seeing this image and you take a picture, and how you're going to reflect this dimension illusion, turning table illusion, depends on your algorithm. So the algorithms run behind and gives you this dimension illusion in the pictures. This is a checker shadow illusion. When you look at this image, the image looks darker under the green block. But in the reality, whites are the similar shades and darks are the similar shades. When you look at it in the matrix format that I gave you, all those pixels have the same value. All the whites have the same value, all the darks have the same value. In order to be able to have this sense, you need to be able to implement some noise in your images, and you use this checkerboard shadow illusion techniques in order to implement this. The last one is the Amos room. That is very similar to what I showed with the Eiffel Tower that you can hold in your hands. Is that this guy looks very tall, but when the room is positioned such that you're looking from an angle, and the tall guy is the closest to you, so you're seeing that person very tall, like giant. But in reality, the person is exactly the same height as the other guys. So three of them are the same height, but the angle of the room is giving you that illusion. And that's also the theory behind the modern camera technologies and theory behind some of the image processing algorithms that we use in today's world. Any questions up until now?
Nothing at the moment. So yeah, I think we can move on. But don't forget to put
Awesome.
the questions in, guys.
Awesome. Yeah, so the reason that you don't see these is because of the computation and the storage power. Even though we talk about the cheap computation and the cheap memory, we're still at a stage to come to the point that we can leverage all these algorithms. So initially they were the victim of not having enough data, lacking of storage, and easily approachable tools like open source software. And now we have all those ready, but we need to go work on the math behind it and uncover the theories to prepare our data better for the better AI algorithms. Like you hear a lot about DALL-E. DALL-E, based on all these years of labeling, understanding the features of the images and understanding the features of the text data. So those are, I mean, there are a lot of rooms to work on this, even though it looks like the hidden part of all those algorithms. The most of those studies are not as generalized as everybody else, someone else can think. So I promised that I was going to share this here. So if you want to see more about the fractals, you can actually go see this GitHub page. It's very easily adaptable, and it teaches ABCs of the fractals. Little bit technology and the references on that. So if you're coming from an academical background and in an image processing role, you definitely use MATLAB. So MATLAB is the initial tool that everybody used in the image processing research. So Octave is a tool which is very similar to MATLAB, but it is open source. So whatever the algorithm you have in MATLAB, you can definitely implement those algorithms in Octave. Their performance are similar. The second algorithm, so you can download it from that website and some starter code if you're familiar with the MATLAB. It looks very similar to any other Python or R languages as well, but it is very like you can open this monkey face and then put some convolution and then fit it in this image here. That's what I am doing, and I'm smoothing the corners and the colors. So you can use these simple algorithms just to understand your image and then learn from it. If you're more excited about our studio, you can also download your RTran, and you can use similar code base to look at the similar images. And the other players, the biggest player that I like is Python, because Python has a lot of IDs and more collaborators. And these are if you like the graphic interface, Rodeo, Spider, Jupyter are the interfaces you can use. Rodeo is very similar to Octave and MATLAB. So you can pick whatever the direction you want to go. Sometimes I really go with the basics of basic Python. I just run the Python on my terminal, but sometimes if I want to go very visual, I use these tools. And there are some domain-specific tools. Obviously, Spark is one of them, Hadoop. My favorite here that I want to point out is Tesseract, OCR, and OpenCV. OpenCV is an image processing tool, which is actually, when you call it with Python, it comes as CV2. So CV2 is built on, written on C++, and it is also maintained on C++, but it has interfaces for Python, Octave, and R again. It's very powerful tool. It can do everything, all the processes that I have talked up until now. For the illusion and fractals, you need to get little creative and put some functions together, but it can do that. And the tesseract is the other powerful tool. If you're dealing with a text and the image together, and you don't want to use any hate software, you can actually separate your image and the text using Tesseract OCR and OpenCV tool. So these are actually the interesting part of these two tools. Those are basically the backbones of the DALL-E that Google developed right now. Google used to use Tesseract for their text analysis, and initially it was paid, but they open sourced it, and it's still, even though it is open to the public and there are still bugs, it's a great tool to start. So these are the OpenCV functions that you can implement. You can work with 2D, 3D image. You can also work with the movies, ego motion estimations, object detection, segmentation and recognition. That can also give those depth, as I mentioned, the illusion depth, but you need to get little creative or there, and structural motion, and augmented reality. And recently, they are working on a product that will allow some real-time virtual reality implementations as well. And you can go check the Wikipedia on OpenCV for more functions, or you can go check CV2 as well. Let's go back and give little bit details on the steps, like the main steps to analyze the image. First one is basically raw data. So this is the image that Lena was holding. And first step is preparation of the data. Basically, here you see a threshold. You see two different fuzzy thresholding and black and white thresholding, and then feature extraction. So here we extracted the edges in that image. So I'll talk about those. And classification or clustering is the last step, but I am not going to touch base there here. And if you're tired of Lena, you can also use this gentleman. This gentleman was as famous as Lena for the starters. And obviously, new generation is very sensitive to and respectful to Lena. So there are a lot of works, and this is one of the best works that I saw on GitHub about the cameraman, and you can go see what can be done with this gentleman here. A little bit fun fact, this gentleman took Lena's picture. So it's interestingly, the same gentleman's two pictures became very famous. Yeah, let's get deep dive into the thresholding. So the thresholding is basically reducing the image to one color channel. What it means is that your image will turn into black and white. And then this B is going to be your actually thresholded image. And the other way of approaching this, you can play with it, but I call it clipping. This was the approach that we took 20 years ago that nobody took. So you can see how fast this field is moving. We actually define moving average threshold. So we looked at the windows, 6 to 6 windows in the matrix, and identify the moving average windows, and then turned everything under that threshold value to black 0, and then keep everything above that in their color tone. So the colored image became a grayscale image, but we still saved from the algorithm cost and the storage cost. So that was something very important finding back in the days. And I see there are a lot of different windowing techniques that you can add in your thresholding. One of them is called Pascal Gaussian windows. These lists go on and on. So this is actually another black and white thresholding technique. This image that you're seeing with the rhino is actually very complicated, but at the same time it's very easy. So it's basically, there is one threshold because everything is gray, and when you take that threshold, it becomes very, very dark, like back in up here. But the good thing about it, you can still see the edges. Then you go one step further, and then you end up having like second thresholding will give you the edges and lines, so it becomes more of a caricature image. And then here are some of the thresholding techniques. One is global thresholding. That's what we implemented with that image. So you find a threshold just adding up all those pixel values and dividing. Let's say you have 100 pixels, and then you added up 100 numbers in your image and divide in 100, and that's your threshold. Everything below your threshold becomes 0. Above threshold becomes 255, which is white, and you ended up having black and white image. Local thresholding is basically you pick small windows out of your 100 to 100 image, and then find local little thresholds, and each window will have a threshold value, and you can do same black and white thresholding. But here you will hear something, that windowing effect. You need to be very cautious. The other one is the histogram. So you take the histogram of your entire image, the pixel value of your entire image, and then you pick median, like here, some value, and then let's say keep these two higher values and put everything down to 0. So that's another approach. Offset threshold is another thresholding method that requires some more approach, and it is in between moving average and the histogram, but that's also very successful method. Gradient based approach, you actually look at the smallest, take the smallest value, and then move your pixels to that smallest value, and whatever your smallest value is, you start grading your image. So that's called gradient based thresholding. Clipping, I mentioned a little bit that everything above your threshold, it's very similar to global thresholding, but everything above your threshold keeps the color. So it's basically a fuzzy logic algorithm. Any questions up until now?
We have one, and it is, can you expand more on why fractals are important to understand for computer vision in a practical sense?
So the fractals are very important because you can compress your images. Let's say you want to run a big algorithms and you came into a business that they have been collecting the data for 100 years. Like, let's talk about the caterpillar, that they deal with the small parts and pieces. And let's say they want to optimize their inventory. So they took these pictures last 60 years, and they put these pictures in different places. In order to be able to analyze this data, you first need to find a feature that you can use for your algorithms. Second of all, you need to have a cost-effective way, which is storage and calculation way to store this data. So when you find the smallest possible, which is the scalability aspects of the fractal, smallest possible pattern in your image, and then keep it as your key feature, that will give you a lot of opportunities to play with the algorithms and implement like one-by-one matching or one-to-many matching on this particular problem. So that's why it's very important that you can scale and you can compress your data.
Perfect. That's the only one we have.
Awesome. This is for the people who really likes the set theory, because morphology is all about the set theory. It is all about intersections, unions, set differences, symmetric differences, and Cartesian products. And I'll talk about a couple of the methods here. So one is the dilution. So basically, this is the original image. When you dilate the original, when you use dilation, which is the set theory, you're dividing your image. So you dilate, you have a, this is the, let me go back. This is the intersection, and you end up having this dilated image. And the second one, the other one is the erosion, which is basically you're looking at the unions, and then you ended up having a larger, darker side because you're taking the union of your 0 pixels. And I guess I can talk a little bit about this, but it's basically just using the similar method as we talked in the thresholding, but instead using some set theory. And these are, going back to this, these are the most common used algorithms in that. Union and intersection and the set differences are 3 main theories that we use. So you can implement the union, and on top of union, you can implement intersection, or you can implement the set differences, and then you start having your core image. So core image being your features. So this original image and the dilated image, when you look at them, the template, the skeleton is not changing, but it is more compressed. So that's why it is more important also represent the letter better. Also the erosion. Erosion is when you want to really bring up the foreground, background being black. You use the erosion, so you erode your foreground, which is the white pixels here. So depending on what you want to do at the certain point, you implement those, like these are the different versions of it. You implement those theories and then end up having better images or better features for your aim. It's like learning from images are the best thing that you can do. So these algorithms, there is no one way of really implementing it. You just start learning from it. You start feeling that what is the best method for the processing, honestly. And these are like the further transformation. We talk about dilation, erosion. There is opening, closing. Those are the different versions of dilation and erosion. Hidden mistransformation, thinning. That all thinning also uses some power functions, thickening, skeleton, medial axis transformation. These are all different versions. As long as you know this dilation and erosion, you will be able to do other transformations, but I highly suggest that you go and check those algorithms. Any questions here?
Yeah, we did just have one come in. So these techniques can be used for augmentation to increase the data set for training purposes. Is that correct?
Yes, definitely. And the other way you can do is if you don't have enough data sets, and if you want to simulate more data set, you can use morphology. That's great way of adding the noise to your training set and also understanding the quality of your future like classification or clustering algorithms.
Perfect. That's the only one.
Awesome. And the last part is the bonus part that I wanted to give you. The convolutional neural networks and the deep counter. These become very powerful when you complete the steps that I think I see people on the chat, but oh, okay. So these become very powerful when you clean your data first. And the basics are like for the neural networks are basics are literally like how your brain works, how the cell firing rates work. And you have certain inputs, and then certain inputs trigger certain cells at certain weighting factor, and then those activate certain outputs. Like for example, I'm hungry. It's like you're sitting between the time between me and my dinner, and I'm watching my dinner, for example. So the certain like my attention moves to one direction, and then I start thinking about food, the smell. So all those different parts of my brain gets activated, and the weighting factor of this activation depends on what the action is. And that's the same with the images. So this is the basics where we are coming from when we talk about the neural networks. And this is the one cell that you can take as basics of your algorithms. So convolutional neural networks is also like taking a part from your image and then looking at the feature maps and getting the maps pulling and then layering the features on top of each other until you find the perfect match. So basically what you're doing is that you're running the algorithms, you're firing different cells constantly, and you're finding the like the algorithm itself is finding the right correlations of these cells together. So you can think about the convolutional neural networks in that sense. So this is how it works. You're actually using a window, and this window is on the left, and then you're moving this window until all those windows become red, or you take the averages, and then that gives you the filter for yourself. So it's basically you have a starting window, and then that you move that window back and forth until you find like the best average firing rate that you're looking for. So that's how the algorithm itself works. And this is like an interesting project that I involved in the past. So they asked me they told me that they have a lot of images and they want to understand the price of the certain burger item. And first step is just digitizing the images. And as I mentioned, we had a lot of different cameras. We have different angles. So the first thing we did, we found the average DPI for all the images, and then get the average DPI. Then we had to really simplify this image and separated the images from the text using Tesseract. And then we ended up having the price, name, image, and order and noise factors with the convolutional neural networks. And then we took out the images, and then we got the name of the burgers, and then the price of the burgers, as well as the color accounts. And in this project, we used all the available open source products, like Tesseract that I talked up until now, Deep Counter, and you can see that article, Python, and OpenCV. So this is like what you can do with the information that I have given up until now. Thank you. I'll go back. If there is any question, I can take.
Yeah, perfect. So we've got one final one from Usman. So a lot of algorithms seem to focus on picking out single channel features like edges, curves, etc. by compressing a 3-channel input space into a single channel input space with thresholding. What are some techniques that focus on extracting color features or patterns between channels, i.e. color relationships in an image?
One of the things that you can do, look at the fuzzy logic algorithms, or here I talk a little bit about that, but for the simplicity, I only gave you a couple of basic algorithms. But if you look at the odds thresholding and then keep your color, RGB color, above the threshold value, you can pick your threshold color, whatever you want, and then implement the odds thresholding. You will still keep your coloring or the histogram. You can define whatever the threshold that you want to give to your histogram. Then you can pick your RGB, the main 3-channel colors, and then take out whatever the information, color information that you don't want. But with these algorithms, like other than this global thresholding, you can definitely, even with the global thresholding, if you do clipping, you can still keep your colors.
Perfect.
It all depends on your threshold, and it all depends on how you're approaching to your data.
Perfect.
I would definitely suggest, like, if you go look at the name of the book is Fuzzy Logic by Bezdek, Bezdek. The way that book approaches the different ways of thresholding will give you a lot of good ideas how you can keep your colors.
Perfect. That's great. That's the end of the questions from the audience. I have one question for you, Meltem. It's a very simple question from a very non-technical person, but what's the most innovative way you see computer vision being used in day-to-day life? Because I see it all the time in like sports, for example, like Hawkeye and the big one with obviously autonomous vehicles. But yeah, what's the most innovative way you see it being used?
I think like I wanna answer this like from a different perspective, because we are all focusing on like the generalized ways, but most of the problems that we are defining and you're defining is like the hockey. You know, hockey is all about like how quick you move and how deep you go, and then how much the, you know, how much how close you are to Pocky and things like that. So that's very, I mean, that's very easy to identify. It's called weak AI, because you can have a lot of images in your database and understand what is the good move. And medical field is one of the other fields that image processing is going to get a lot of attention, because we already collected a lot of data in the image perspective. That will be very important cancer analysis. And the other thing that I like, it's called generalized GAN models, GANS models, with the marketing. You can actually use these generalized algorithms to create like, there's little Michaela, which is an Instagram character, goes everywhere. That's another like very innovative way where you can actually decrease the waste, like traveling for advertisement. Instead of traveling, you can actually develop these GANs models, or another approach is VR, AR approaches in an environment. You can advertise, like I'm sitting here in Austin, but you can advertise something in real time in Hawaii using these GANs models, putting me in that environment. I think those are going to be like within 5 years, those are going to be the image processing computer vision implementations that we are gonna see.
Perfect. Yeah, I love what you said about the healthcare sector there. I worked with a company back in London who were all focused around computer vision and image processing to detect early signs of breast cancer. So love seeing it in areas like that, which is having a massive positive social impact and obviously saving lives at the end of the day. So yeah, but yeah, that's all the questions from me as well. That's all the questions from the audience. So yeah, thank you so much for that brilliant presentation, Meltem, talking us through the ins and outs of computer vision. I'm sure a lot of people took a lot away from that. So yeah, I appreciate how busy you are at the moment as well. So understand it wasn't easy to take time out of your week and your day to come and speak on this webinar today. So thanks for that so much. As well, everyone that attended, thank you so much for your time and for tuning in. It's great when people get involved as well. So good few questions came in today. So I really appreciate that. And if you did enjoy today's webinar and would like to attend again, please do follow Amicus Recruitment and the live series community page on LinkedIn, and also subscribe to our YouTube channel where you'll find future and past events as well. So yeah, again, Meltem, thank you so much for your time, and everyone, see you again soon.
Thanks for invitation. It was a pleasure to be here. I like these algorithms all the time. I can talk about it day and night.
We'll have you back soon then.
Cheers.
Perfect. Thank you, everyone. Bye.